Welcome back, Year 10. This is Lesson 6 of Physics Double Science course. Quick recap. You should have by now, before watching this video, gone on to Moodle and answered the questions for the starter retrieval quiz intended to activate your prior knowledge and get you ready for this lesson. If you haven't, please pause the video, go back and do so. Lesson 6 today, page 30 to 40, quite a lot to cover. So full concentration required. If we look at the syllabus, it's what we've got highlighted here in green. And we're going to learn how we use circuits to investigate how current changes with voltage. What that means is, if the voltage goes up, does the current go up? Does it stay the same? Does it go down? And we're going to learn that for three different components: for a resistor, for a filament bulb, I'll change the pen, filament bulb, and for a diode. Right, so for a resistor, for a filament bulb and a diode. I'll just underline those three different components. A little bit more detail on that. The circuits could include a variable resistor, and in the example we look at today, we'll be using a variable resistor as opposed to a variable power supply, because we need to be able to change the voltage across these different components, because we want to investigate what the relationship looks like, and you have to learn the different shapes for the different graphs. For the resistor, the shape of the graph looks like that, a straight line. For the bulb's got a different shape, it's got this curved shape here. And the diode, which is a component that we haven't seen before, the shape is like that. So we're going to be learning how to carry out an experiment. This is the main experiment for this topic that you have to learn the method for, and there'll be an assessment to go alongside this lesson for you to be able to confidently go through the instruction text for this experiment. So quite a lot to cover. Just go back at the top. Also, you need to have the knowledge of how R varies for V. That means how resistance varies with voltage for a lamp. Basically, they're talking about these graphs underneath. And how resistance varies with positive or forward bias and negative voltage or reverse bias for a diode. And that normally a diode will not conduct until a particular voltage is reached. So in other words, what it's saying is, for a diode, the electricity will flow in one direction only. And for it to flow in that one direction, the voltage needs to be above what's called a threshold voltage. But anyway, we'll be coming on to that later. Before we go any further then, let's just recap on what we've looked at earlier in previous lessons. So that is, electric current is a flow of negative charges called electrons, and that's what electricity is. It's a flow of electrons through a conductor. A conductor is something that allows electrons to flow. They have to push their way through lots of vibrating ions. The word we use for push, what gives them the push, is the voltage. So the ions slow down or resist the flow of electrons. This is called resistance. There's a diagram underneath that represents a copper wire. You've got to show the pathway that the electron may take past the metal ions. Now, just a little bit more information there. These ions are positive ions. And the reason they're positive is because the electrons that are negative, the electrons are negative because they have broken free of the atom, leaving the ion positive and negative electron. So what you've got then in a wire, in a conductor, are these positive ions and these negative electrons. And the negative electron is being pushed by the voltage from the negative side of the wire, because negatives and negatives repel, like charges repel, so it's pushing that way. And this is the positive side of the wire connected to the positive side of the battery, which is pulling, so you've got a push there, and you've got a pull here from the positive side of the battery or power supply. And the electrons then, they're trying to move towards this positive side, but what happens is that they get attracted by these positive ions. So the more positive ions you've got in the wire, the more difficult it is for the negative electrons to pass by. Now if you think about that, you can think of the variables that affect the resistance of the wire. Obviously, the longer the wire, the more positive ions there are. The thinner the wire, the harder it is for these electrons to find a way, a path through the positive ions. Think of it like a road, cars going down the road. It's easier to get 1,000 cars down a motorway because you've got 3 lanes than it is down a country lane. The country lane's got a higher resistance. What I want you to do now then is to add in a few more electrons and just show these electrons trying to move towards the positive side. Underneath it says electrical push or voltage is the word we use. So let's look at this quick video. It shows electrons flowing around a circuit, and you can see at the bottom you've got a resistor, which is actually been zoomed in on, and that resistance is actually a wire. If we're going to look at that video again, and you can see at the moment the switch is off. You've got these free electrons. Now in the video they're calling these free electrons delocalized electrons, and when they put the switch on, I should say, you can see then that the electrons are pushed from the negative side of the battery, which is at the top right, through the bulb switched on, and the electrons flow through. And in essence, that's exactly what electricity is. It's a flow of electrons, and you can see how the path or journey of those electrons in the resistor at the bottom is being obstructed or resisted by the resistor. And I've just written on the right hand side here what the term we use is free electrons rather than delocalized electrons. So if you're answering that in an exam question, we just use free electrons. Questions 1 and 2 are very similar. It's testing your understanding of what factors affect the resistance of a wire. And I'm going to give the verbal answer, and then you can pause the video and you can write down the answer in your own words. Let's look at question 1. Explain why a thin copper wire has a larger resistance to the flow of current than a thick copper wire. So the variable here is the thickness of the wire. So we've got thick and we've got thin. I mentioned a few moments ago about a motorway in a country lane, and a motorway can get more cars down in a particular amount of time than a country lane would. So the thicker the wire, the smaller the resistance, because there's less obstruction from the positive ions. Question 2. Why would a long nichrome wire, it doesn't matter, don't get put off by the fact that they're using nichrome there and copper there. They're just different metals, but they're conductors, so they allow electrons to flow through or electricity to flow through. Don't get put off by that. That's sometimes the case in the exams. You can fixate on a particular word when sometimes you don't need to. Why would a long wire, just read it that way, why would a long wire have a higher resistance than a short wire of the same thickness? Break it down, make it simple in your mind. Why has a long wire got a higher resistance than a short wire? Well, very simply, because they have more positive ions to avoid, because it's the positive ions that cause the resistance. Question 3, we haven't talked about this variable, about the temperature of the wire. And the answer is the temperature of the wire would affect the resistance, and the higher the temperature, the higher the resistance, because I haven't talked about this yet. These ions aren't staying still, they're actually vibrating from side to side. Well, in all directions, in fact. And the more they vibrate, the more likely it is for an electron, a passing electron, to be attracted into the ion. So the higher the temperature, the higher the resistance. And I'd like you then to answer question 3. Again, just pause the video and answer. Those 3 questions are a little bit like a science investigation where you're asked to keep control variables constant and change one variable. In question 1, the independent variable is the thickness of the wire. In question 2, it's the length of the wire. And in question 3, I'll just highlight it, it's the temperature of the wire. Hot and cold. Question 4, I'm going to do with you. It's a real challenging question. You've got to make quite a few connections in your understanding. It asks, explain why a filament bulb has a very long, very thin wire inside it. Draw in the filament wire as well. So let's draw in that filament wire first of all. The filament wire is a very long and very thin. So in order to fit that wire inside the bulb, what happens is that it's coiled round many times into what's called the shape of a helix, so that you can maximize the length of the wire. You want it long and thin. And of course then what we do, we have these wires are connected to power supply. In the house it will be the ring main circuit, which is what we learnt about last lesson. So that would then go to your live wire, neutral wire, or if it was in a DC circuit, you would just have your positive and negative there in order to push the electrons through. But going back to the question, it says, right, draw on the filament wire as well, done that bit, explain the explanation. I just put down a few notes there to help you with your explanation. Explain why your filament bulb has a very long and thin wire inside. Well, the way you've got to start from the point of, to have a bright bulb, you need this filament to be able to radiate light. Otherwise, there's no purpose in the light bulb. And in order to radiate light, it's got to be at a very high temperature, because the wire inside the bulb is usually tungsten. Tungsten's got a high melting point over 1,000 degrees. So we're actually getting the temperature of the light bulb over 1,000 degrees Celsius inside the bulb. It's radiating not just light energy, but heat energy as well. So we're making the wire glow not just red hot, but white hot. And in order to do that, we need to have a high resistance. And to get a high resistance, the wire needs to be long and it needs to be thin. How does that increase the temperature of the bulb? Well, the higher the resistance, the more collisions there will be between electrons and the ions to generate the heat. You need to pause the video at that point, because you need to write down your explanation in your own words on this part of the booklet. And this really needs thinking through. In reality, you should be rewinding this part of the video 2 or 3 times and perhaps go back to the earlier part of the video to understand this. And if you understand and are able to answer question 4, your understanding is excellent, because this is at a very high level of conceptual understanding, because not only do you understand the flow of electrons, you understand about ions, the link between temperature, resistance, collisions, and the generated heat. So pause and do your very best, please. Okay, I hope that went well. I'll just put a red asterisk next to question 4 as a reminder to yourselves that you need to be answering that. Okay, let's do a quick recap in order to help us answer the next part of the booklet. V equals I times R, voltage is current times resistance. We know that. So if we wrote that down in words, resistance is voltage over current. Nothing new here. Remember, you're given the equations in the exam. Voltage over current. Good practice to use a ruler. Or in other words, V over I. The symbol for voltage is V. The symbol for current is I. Where R is measured in ohms, where I is measured in amps, and V is measured in volts. So I'll put down the symbols and I'll write down the units next to the symbol. Here we go. This means that to work out the resistance of a component, we just need to take a current reading through it and a voltmeter reading across it. Remember, ammeters in series, voltmeters in parallel. Now the reason we're doing these quick questions, question 1 and 2 in a moment, is to build up to the main part of today's lesson, which is to learn how to set up the Ohm's law circuit, and then you're going to be plotting some data and then understanding the different shapes of the graphs for the resistance, a filament bulb, and for a diode. Okay, we'll take our time. Question 1, recap. Remember, ENO, equation, number, answer, units. And remember to highlight the important parts of the question. Current through a bulb is 0.25 amps. Now we've done the E part of the question, which is writing down the equation. The current is 0.25. The voltage, here look, is 9. You divide the voltage by the current, and 9 divided by 0.25 is the same as multiplying 4 by 9, isn't it? So you've got 4 lots of 0.25 in one, so that's 4 times 9, that's 36. But please don't trust my maths, use your own calculator to work out the answer, and put the units there. ENAU, you can work out the answer. Little asterisks. There's a reminder. Pause the video and do that. Question 2. A voltmeter provides a reading of 12.4. We should have in there 12.4 volts. 12.4 volts. Across a wire, and an ammeter in series, given a reading of 0.36 amps. Calculate the wire's resistance. And I think you just need to add in a little apostrophe there, because the bit of grammar for you, the resistance is the property of the wire. So wire's resistance. Okay, so here again you're using that same equation. V over I. Get your ruler. You can do it from there. Just make sure you include not just the answer, but the unit as well. Little red asterisk to remind you. Turn over to page 32 in your booklets. First thing you've got to do is construct a circuit to allow a student to calculate the resistance of a resistor. So you need the voltage across and the current through. Voltage and current readings can be changed either by adding a variable resistor or including a variable DC power supply. So we're going to use the second option. No, we're going to use the first option, which is a variable resistor. Now, a variable DC power supply would be something where you could just change the voltage output from the power supply, and the symbol for that would be the same as a DC supply, with that arrow going through. The arrow going through there is the symbol for variable, as we would use it for a variable resistor. Now, to help you do that, what we've got underneath is an actual picture of what the circuit would look like. I'm not going to label this for you, but I'm just going to highlight different parts as we go along. So you might be able to see in green there, that's our 3 cells connected in series to make a battery for our DC supply. If we come round this wire here, this is our ammeter coming out of the ammeter, so that measures the current. We go through that wire there. This is our resistor coming out of the resistor the other side. So that resistor, I am going to label this part because this is the important part of today. This resistor here is what we call the component under test. Now that component for the course that you're learning could be a resistor, a filament bulb, or it could be a diode. In this first example, we started with the resistor, component under test. Let's just finish off tracing this around. Now this is our variable resistor, so we can change the size of the the size of the current flowing through the circuit by changing that variable resistor. Okay, so that's a quick trip around really our electrical circuit. Oh, I forgot one part off. I forgot this here. This part of the circuit here is our voltmeter in parallel. It measures the voltage across that resistor. So if we know the voltage across and the current through by having our ammeter in series, remember what we do? We just divide the voltage by the current to work out the resistance. So you've got to go from that photograph to a circuit diagram. Now, easiest way to do that is get in your, let's change my pen, is to get in the different components first and then join them up with a wire. So we've got an ammeter, that's this bit here, I'll circle them as I go through. We've got the resistor itself, and that's the symbol for the resistor. We've got a voltmeter in parallel with the resistor, and we've got a variable resistor over here. Let me just circle those different points. So that was our variable resistor, that's our resistor, that's our variable resistor, and again this is our power supply, in this case DC or direct current power supply. Just remember, with the variable resistor you draw an arrow through it, so you know it's not a fixed resistor. And then just get your ruler. Remember, you should be using a pencil and a ruler, and then just join up the components. Okay, so your circuit diagram should look like that. I just paused the video whilst I was recording and added in the wires to the circuit. Check yours against that. I'll put a red asterisk there as a reminder that you needed to have done that yourselves. Now we're going to look at using this circuit. It's called the Ohm's law circuit, and see what that looks like in a real life experiment. Turning over then to page 33, this is the top of page 33, Ohm's law. It asks, what happens to the current flowing through a resistor if we change the voltage or PD across it? So as a starter then, the component under test in this case is a resistor, so that goes there. And we just label ammeter, voltmeter, just as we've done a few moments ago on the previous page. We put in our wires to join the resistor to the rest of the circuit. So to do, complete the circuit diagram, just done it, and collect data for voltage and current by turning the dial on the variable resistor or using a variable DC power supply and using the formula to find the resistance of the resistor in ohms. So what you're going to do, we're actually going to watch a video. Myself and Mr. Hancock have done this experiment, and we've recorded it as well and taken down the values of voltage and current. So for example, let's say we recorded 4 volts and 2 amps. 4 divided by 2 would give you 2 ohms. That's what we've been asked to do, but the numbers won't be as straightforward as that. So what you need to do now is watch the video, and then you'll be filling in this table at the end of the video. What you're looking at here can seem a bit daunting at first because we've got many different components. So I'm going to use a pencil to point out the different components and then just hold up a circuit diagram to try and make sense of the circuit. Okay, so firstly at the top we've got our 12 volt DC power supply. That is this component here. Mr. Hancock, if you could just hold that up please. Okay, so here's our power supply, and if we trace out of the power supply, we go along this wire, we then go straight into our ammeter, which we see here. Remember the symbol, I have a spare ammeter to the side here, and that's the symbol for the ammeter. We then, if we trace out underneath the ammeter, we then go to the component under test. Now in this circuit diagram, yes, we have a bulb or a lamp. We are going to be using a resistor, and you can see the symbol for the resistance there. So we come out of the power supply, through the ammeter, through the resistor. Don't worry about these wires for the moment, which go to the voltmeter. So we're going through the bulb, or in our case, the resistor. And the symbol for the resistor is that rectangular shape. We carry on and then we get to our variable resistor. So our variable resistor is just here, and the variable resistor is something that allows us to change the voltage across and the current flowing through. So as Mr. Hancock is demonstrating beautifully there, you can slide the slider both ways and that will vary the voltage on the voltmeter here and the current on the ammeter here. So what we need to do is change the voltage across the resistor and measure the current through it. And what you need to do then is, in your booklets, I'll just hold the booklet here, we are going to be recording the voltage and the current here. We're going to take 6 readings going down, and then you're going to calculate the resistance in this final column. And what we should find is that the value for the resistance here should be approximately the same. Then underneath the table, of course, you're going to be plotting the graph. Notice the graph has got both a positive and negative axes. So what we'll do in our table, we'll take some positive voltages and some negative voltages so that we can plot both sides of the axes. Okay, so we are currently, if you look at the voltmeter here, and I'm just going to move that wire out of the way, we're around about 1 volt. It's fluctuating slightly, but it's as close as we can get it to 1 volt. And the ammeter is reading, if we move the camera around, move that wire out the way, is reading 0.2. So what we're going to enter here on the table, at 0 volts we get 0 amps, but at 100 volts we are getting 0.20 amps. And if you divided the voltage by the current, and I'll do the first one with you, if we hold this up here, you would divide voltage by current, 1 by 0.2, and you would write 5 in there. But we're not going to do those during this part of the video. Okay, we're now going to change the voltage to 2 to 3, and then negative 1, 2, and 3, and take the results. So Mr. Hancock now is just moving the variable resistor. Great work, sir. He's got that at 2.01. So I'm going to be writing that value for voltage now into the table, 2.01, and the current is 0.43 3. And I'm going to hold that table up to the camera as Sir then changes the voltage to as close as he can get for 3 volts. So you make sure now you copied that down into your booklet. And that's great, sir. We've got there 3.00. Yes, it's fluctuating again. And the current is reading 0.67. 3.00, 0.67. Okay, so we have got a value of 3.65 and 0.82. So I'll write that down, 3.65, 0.82. And we're now going to take some negative readings. Hancock now has kindly changed the polarity on our power supply. Remember, that's our variable DC power supply. And you'll notice straight away, as Sir's pointed out, I'll just move here so we can see that the readings now have become negative. You can notice there's a little negative or minus sign just in front of the values on the meter and on the ammeter. Remember, voltmeter in parallel, ammeter in series. So what we'll do this time, we'll actually start, Sir, perhaps at that value there, minus 4.28. We've got minus 0.96. And then Sir's going to move it down to somewhere close to 3 volts, minus 3 volts I should say, and minus 2 volts. Hasn't got to be spot on, but we'll get as close as we can. It's jumping about a little bit. Okay, let's leave it settle there then, Sir. We've got minus 3.42, minus 3.42, and we've got minus 0.76. And we'll take one final reading. As Sir's doing that, I'll just show you the table, which you need to have in your books. And here we've got one final reading. Oh, well done, sir. We've got minus 1.99 and minus 0.45. Okay, so what you need to do now is use those values we have there, fill in the third and final column for resistance, and then plot a graph of voltage against current. Remember, independent variables go on the horizontal axis, so the voltage on the horizontal, and current is what's being measured. We're changing the voltage, we're measuring the current, so current will be on the vertical axis. And what you should get is a straight line graph that goes through the origin here, because when your voltage is 0, the current is 0. So you should have a straight line graph going through. Now, just before we finish, let's look back at this circuit again. We could have very well done exactly the same experiment and just change the component under test. So we could just change that fixed resistor for a different component, in this case a bulb. Ooh, we're at minus 7.3 volts, sir. I might blow the bulb. Can we go down, perhaps use the variable resistor, fine. If we go down below 6 volts, then that bulb should come on. And again, we could do exactly the same experiment. We could change the voltage as Sir's changing the variable resistor now. You can see as the voltage is changing across the bulb. Right, so it's minus 3.36 going down. You should see the ammeter on the right hand side which is 0.04 at the moment, or minus 0.04, changing as well. It's just dropped down to minus 0.03. There's three different components you need to learn the shape of. When I say the shape of, the VI, or voltage current graph, it's a straight line for a resistor, it's a curved shape for a bulb, and the shape for a diode is characteristic that it goes along the horizontal axis and then a sharp increase at the threshold voltage. Look at that later. Okay, so that video would have shown you how to do the experiment and how to record the results. I've taken a quick screenshot of that video and put it to the right hand side of the table that you now need to fill in, and hopefully you can decipher my scroll. Apologies for that, I was trying to hold a piece of paper, write down the results and record at the same time. So if we take one of those at a time, like that's 1.00, what you do is just write that here and 0.20. What you do after each one of those is work out the resistance. The resistance is voltage divided by current, and I'd like you to give the answer to 2 decimal places. I'm lucky here, look, that I got nice easy numbers to work with. So that's 5.00 for resistance. So just pause the video now and complete the rest of the table. The second row, then you need to divide 2.01 by 0.43. I'll do this down the bottom right hand side of the screen. Divided by 0.43. Now that's come to came to 4.67 to 2 decimal places. I'll do one more. So this is 3 divided by 0.67. That comes to 4.48. So what you see in here is that the resistance is pretty much staying constant. There's a slight decrease, and that's probably to do with perhaps a change in temperature or just possibly accuracy in readings. Now, when you've completed that table, I want you now to pause the video and complete the table, and then to plot the graph. So just pause. When you fill that table in, it should look like that, with the resistance calculated to 2 decimal places. What I want you to do then is to plot the graph of voltage against current. Just move this out of the way. The title of the graph, look, is saying a VI graph, that's voltage current graph of a resistor at constant temperature. When working out the scale of the graph, what you need to do is look at the highest voltage, which is on the positive axis, 3.65, and the negative minus 4.28. And for current, you've got to go up to at least 0.82, that's the highest positive, and minus 0.96, the negative axis. Voltage goes on the horizontal axis, so you can label voltage on the horizontal. We're changing the voltage, So that's almost like an independent variable that would go on the horizontal axis. And we're measuring the current. It goes here. What we're trying to achieve here is to understand the shape of the graph for resistor, and then for a bulb, and then for a diode. If we go back to the start of today's lesson and we look at the learning objectives, these are the three different graphs we're looking at, and the one we're looking at now is for the resistor. So what we would expect, voltage on the horizontal, current on the vertical, that when we plot our points now, we'd expect this type of linear relationship between voltage and current, meaning that when we increase the voltage, we increase the current. Let's go back down then to the page we're just on and think about what it is we're trying to achieve and how we're going to do that. And we do that by obviously plotting the points. So I want you now to pause the video, work out the scale, and then plot the points. Okay, I'm just finishing off the scaling of the current axis. The voltage axis worked out lovely actually, because you could go every large square, we've got 10 small squares inside, look, goes up 1 volt. And for the current, the maximum is 0.82, 0.96 either side. So that works out nicely as well. We just put in 0.6. We can go up in 0.2s for every 5 squares. Just like that. Then you do the opposite when you go on the negative axis. So -1 and so on. So just pause the video now. Carry on with that. When you're plotting the points, take a pair of points at a time. I'll just use a different highlighter. So if I'm plotting 1 volt against 0.2 amps, when you're plotting the points, obviously you should be using a pencil. I'll just use a different color here to make it obvious what I'm doing. So my 1 volt and 0.2 amps, well that couldn't be easier, could it? Because I'm going up from 1 volts, so I'm going up there from 1 volts, and I'm going across from 0.2 amps. I'll do one more, so I got 2.01 and 0.43, 2.01. More difficult. If we think of the scale here, that line there is going to be 2.10, not 2.01. 2.01 is just the other side of that 2.0 line. So I'm going to go up from, I've forgotten what the other number is now. If we go back up to the table, okay, you can see it's 0.43. It's always a good idea to use a ruler when you plot in these points. So 0.43, that's 0.42, that's 0.44, so 0.43 would be in between. So I'm just going to make a little mark there. So I would plot that point just about there. Okay, pause the video. Remember to do the same for the negative quadrant of the graph as well. And the last point, 1.99, minus 1.99, minus 0.45, just plot in there. Now, you should be using a pencil, of course. When you come to draw the line of best fit, it needs to go through the origin. The reason it needs to go through the origin is because when the voltage is 0, the current is 0. So line of best fit, so what you're trying to do here is find that line where it's going through as many of the points as possible, but also you've got the same number of points above and below. So when you look at that, you've got 2 points just above. I'll quickly highlight. You've got one there and one there, which is okay. But if you really wanted to improve slightly, if you could just, still keeping on the origin, could you include those points just by going up a fraction, which means you would need to increase the gradient ever so slightly. So let's have a look at this. The good thing about a pencil, of course, is if you drew that, you took the ruler away, thought, okay, I don't like that. You can always rub it out and do it again. I like that line because you've got 1 point just below. That one's very slightly below. We got one just above and one just above. So that's a good line of best fit to have. The next part, or the next page I should say, turn on to page 34, a few questions. What was the actual resistance of your resistor? Now that's going to be difficult for you, but it was a 5 ohm for you to do because it was a 5 ohm resistor. I'm not sure if I pointed that out on the video or not. It's usually labelled underneath. Next question is a 4 marker. 4 marks. Describe the shape of the graph. Here's that instruction word, describe. Describe different to explain. With explain, you're given reasons, scientific reasons. With describe, you're saying what you're seeing. Look at the shape of the graph, link in the variables. Mention the term origin. Now the variables are our current and voltage. And the shape of the graph, so we can split this right down. Let's use the highlighter again. So variables, we need to include our current and our voltage, explain how one affects the other. We also need to describe the shape of the graph, easy, straight line, and mention the term origin. So again, what I'm going to do here, I'm not going to write this out for you, but I'm going to verbally go through the answer, and I want you then to write down in your own words the answer to get those 4 marks. To get the 4 marks, probably 1 mark for describing the shape of the graph, 2 marks for describing the relationship between the voltage and the current, and 1 mark for saying that it goes through the origin. So if I just go through that, then this could be a type of answer. The shape of the graph is a straight line going through the origin, 2 marks. The graph shows that as you increase the voltage, so does the current increase. And then you would have hit all 4 of those marks. The shape of the graph, the origin, and you've described the link or relationship, is a far better word, between voltage and current. The Ohm's law, discovered by George Ohm, states the current is directly proportional to the voltage applied. I'll write that down. This is a definition you don't need to remember for the exam, but I'll write it down anyway. Current is and directly proportional, not inversely proportional. Directly means, of course, that if one variable goes up or increases, so does the other. Current is directly proportional to the voltage applied. I could say across a wire or an, it would be technically correct, an ohmic conductor. An example of that would be a wire. would show that like this. And I just think of it in these terms: if the voltage goes up, the current goes up. We can simply show that again through this straightforward simulation. If the voltage increases, look what happens to the current underneath. 16.3, 16.5 milliamps, 16.7, voltage 8.8. If we take it right down, current's getting smaller, 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 smaller. Can you notice as well, in that resistor, which is that red cylindrical shape towards the bottom, the little black dots there are representing the ions obstructing the flow of the electrons. So if I increase the resistance on the right hand side, look, we're increasing the number of ions. When we reduce the resistance, we've taken away the number of ions, the voltage is staying the same, and the current's increasing. Ooh. Now add those two lines, P and Q, to your graph. Just be careful with the slope of the graph, making sure that P has a shallower gradient than Q. So make sure that you draw that in. Shallower gradient. Yeah, be careful, mind your P's and Q's, of course. And the question's this. So I'm reading from above, I'll highlight it as I read it. Components like fixed resistors normally have a constant resistance. We call these ohmic conductors. Other components can allow resistance to change, but more about them later. So we'll be learning about components such as thermistors, whose resistance change in a different way with temperature, or LDRs, light dependent resistors, whose resistance change with light. Again, something to look forward to for later. Turn over to page 35, please. It says the following components have VI graphs where the current is not directly proportional to the potential difference. These are called non-ohmic conductors. What you need to do now is draw out below the circuit diagram that could be used to collect current and voltage readings for a bulb. Remember to include a variable resistor and batteries. What you're doing here then is exactly the same circuit diagram as, it could be that one or the one that you drew there. The only thing you're changing is the component under test. And the component under test is this here. In that first example, of course, it was a fixed resistor. In this one, on the next one I should say, it needs to be a bulb. Okay, I just copied that circuit diagram, and all I'm doing is changing that resistor to a bulb. Let's try again. A bulb. And make sure those wires touch. Now I'll let you read through the next paragraph. What you're being asked to do is to use this data and to plot a graph on the next page, on page 36. But as well as plot those points there, what you need to do is create an extra column or two columns for when the bulb is in reverse bias. Let me explain what that means. Negative voltage are called reverse bias. says plot the reverse bias results on your graph as well. So you're plotting this table here. To plot reverse bias, all you need to do is put a negative in front, negative sign in front of each one of these. So all you do, the first one can be 0, 0, next one 0 minus 0.5 and minus 0.11. You get the idea. So you carry on now for the rest of that table and just pause the video. Plot the axes similar to shown there on the next page. I just copied that graph off page 36, look, next to the data there on page 35. So again, what we're doing here, we're taking a pair of data one by one. No, so obviously there's the first two. So I'll plot those first 2 points. First one's straightforward because it's 0, 0. Plot that at the origin of the graph. It goes there. And next was 0.5 and 0.11. So I got 0.5, which is here, and 0.11, which is there. Next one, let's get rid of these two negative signs there, we don't need those. 1 and 0.2. 1 and 0.2 goes there. I'd like you now then to continue to plot those points, and when you've plotted the points, play the video again. And the last point, minus 5 and minus 0.37. Now you should have a graph then that looks like that. It's more difficult to plot this graph because it's a curved graph. You do have a linear relationship, look at low voltages here, but what happens is because as the voltage increases, when you go above that 1 volt, the temperature of the bulb starts to increase, therefore the ions vibrate more, the resistance increases, and what we have then is this curved shape of the graph, and it's exactly the same going here, the way we have this curved shape here. So and you can see after about 3.5 the size of the current doesn't increase, but the resistance is increasing because the temperature of the graph is increasing. Moving on then to top of page 37, applying that knowledge to a question. Extract data from the line graph above to prove using R equals V over I that the resistance in this filament bulb increases from 0.5 to 2.5 volts. See, what you need to do here is calculate the resistance at those different values, and you could do that here. Resistance at 0.5 volts, resistance at 1.5 volts, resistance at 2.5 volts. You can work those out. If you haven't got space to the side in the booklet, you can always do it in the first couple of lines here. But the way to work that out, of course, as I'm sure you know, is you divide the voltage by the current. So at 0.5, if we take this point here, we go up from 0.5 and across to 0.1. we divide 0.5 by 0.1, and that will give us 5 ohms. So what it's saying down here is, extract the data to prove that the resistance increases. Look at the keywords. Use data to prove the resistance increases. So what we should find now is that when we work out the resistance here and the resistance here for 1.5 and 2.5, the resistance would have increased from 5 ohms. I'll just do 2.5, and then I'll leave the rest of the question for yourselves to complete. So at 2.5, I've gone ahead there, I've taken the current reading off at 2.5, it comes back as 0.17 amps. There it is there, and here it is on the graph. Notice the resistance has increased to 14.7 ohms. You work out what's a resistance of 1.5. What you should see then is as the voltage increases, so does the resistance of the filament bulb. I'll leave you to answer that question there. Underneath it asks, why does the resistance vary with voltage in a filament lamp? Please try to include, I'll put a few keywords here for you to include. Talk about how the vibrating ions will change with a higher voltage. The ions are going to vibrate more because you'll have more current flowing, the temperature will increase, the ions will vibrate more, and so the resistance is going to increase. Then just finish that passage at the bottom of 37. Now page 38. It's an instruction text question. It's 2 parts. You're going to write down, handwrite your draft here, and then you're going to complete the written assessment on Moodle, which is lesson 6, Ohm's Law written assessment. It'll be there waiting for you in Moodle. You can practice in draft, so instruction text 1, 2. Remember to use those verbs, those bossy verbs. We call them imperative verbs. So if you look over here, this is taken straight out of the syllabus. This is going to help you look back through the video at the experiment we did earlier with Mr. Hancock helping. Look at these verbs you could be using. Connect the circuit, adjust, record, repeat. Now, include as well our risk assessment, how we go about making sure that the experiment is safe, the hazard, the hot lamps. The problem with hot lamps and the risk to ourselves is the burning skin on the hot lamps. What control measure do we put in place? Allow the lamp to cool before touching them. So you need to obviously pause and look back through this video and earlier on in the video to answer that. Here's our success criteria. Make sure that you've included the equipment that's required, the method, measurements, hazards, just mentioned that it's coherent. So this is again looking at the quality of your written communication, and spelling, punctuation and grammar, SPAG at the end there. Now, moving on to the last part of today's lesson, that third and final graph is for a diode. We've looked at the graph, the voltage current graph, for a resistor and for a bulb. Now, a diode, it's a component you probably haven't met before, but might have heard of. Any of you that do engineering in Gower College, electronics, you might have used this, or even when you're doing electronics in D&T earlier in the school. What is a diode? A diode is a component that allows electricity to flow in one direction only, like a one-way system around the school, a one-way street, it can only go one way. We also have special types of diodes, an LED, a light emitting diode. That's the symbol for a diode. These are what diodes look like in real life in an electrical circuit, and underneath there are light emitting diodes. You see LEDs everywhere, remote controls, TVs, electronic systems. These are just the different parts of a diode, but what I want to draw your attention to, importantly, is forward bias and reverse bias. Forward bias is when the current is flowing in that direction. Reverse bias that way. No current flows in reverse bias. Current does flow in forward bias. You might have heard of these terms anode and cathode before if you've done electrolysis in chemistry. The positive side and negative side of the diode. Okay, what do you need to do now? Well, we need to set up that Ohm's law circuit, or draw out that Ohm's law circuit, and this time our component under test is the diode. So if you look at the previous pages and find that Ohm's law circuit, I've just copied one in there now from previous pages, and what we're doing this time, we're changing the component under test here again. It was a resistor the first time, then it became a bulb, and this time we want to change that bulb to a diode. Let's remove the bulb component under test and then put in the diode. Now, there's a right way and a wrong way to put in a diode, positive, negative from the battery. So when we put the diode in, we need the diode pointing in the correct direction. That's what we call forward bias. We could do the same experiment again, vary the voltage, measure the current. So this is a voltage current for a diode. Can't spell. Let's correct that. Now the shape of this graph, I'm not asking you to plot points from a table. Effectively what happens is, if we were to carry out an experiment, it would look like that, where in the reverse bias there is no current, but then we get this shape because above a certain voltage called the threshold voltage, voltage is usually about 0.7 volts in most diodes. So approximately, that's the symbol for approximately 0.7 volts. You don't need to Remember that, by the way. It's just for your information, for your knowledge. Now, just to finish off the lesson, you need to make some notes on diodes. Do some research. A good website to go on to would be BBC Bite Size. There we go, there's the example there. If you just Google diodes BBC Bite Size, you can use that particular page, or just pause this video with that information. And that's it for lesson 6. Now, certainly the most challenging lesson so far, and I would argue perhaps the most challenging lesson during the whole of the year 10 physics course, and possibly so compared to year 11. So don't be downhearted if you don't understand first time. Just listen to the video again, rewind it, and there will be videos to support this learning in Moodle. And just make sure you've, as well as doing the starter retrieval quiz, you do the plenary assessment to give you some feedback of your knowledge. And finally, make sure you've completed that written assessment so your teacher can give you some feedback on your knowledge and understanding. See you next time. Bye.